Hello, this tutorial is about optical production control for large area coaters, and actually I've shown you in previous video tutorials something about the basic thermal and optical functions of glass coatings, and there was also the topic of the design. And here we end up with a typical design situation for a double silver coating where we had wishes for the transmission and the color. And suppose now we want to turn this into production. We want to push this design to be a real coating product that your company is going to sell. And this tutorial will show you how we can use optical spectroscopy to watch the production and make sure we are producing the right coating. So let's take a look at a typical large area coater. Here is a setup for a double silver layer where we produce the bottom oxides with two deposition stations here. First silver layer, then the center oxide with several cathode groups producing this very thick oxide, then the second silver layer and the top oxide. So unfortunately, if you use large area coating equipment like sputtering devices, they are not really stable in the sense that you switch them on today and they produce exactly the same coating as they did yesterday. So every coater has its own special features. In particular, if you have opened it, broke the vacuum, and you start it again, then everything is different, and you don't really know how the coating state is at the moment. So actually, you don't know really what you produce. And if you want to answer the question, do we have to change some of the layers? You have to get some extra information about what you are producing. How can we get this extra information? Actually, what you typically have is optical inspection setup at the end. Typically, that's a traverse system that measures the glass side reflectance, the film side reflectance, and the transmission at several positions on the glass. Usually, you have a scanning system that moves when the glass pane is underneath, that moves along and measures every 10 centimeters or so the optical spectra. So that's what is present in almost every coater that I know, and what you then have basically is are the transmission and reflection spectra. Actually, I want to make some remarks about the spectrometers that we are using here typically. In a coater, you have typical cycling times of 60 seconds or maybe even 40 seconds. And if you want to measure something like 30 spectra, you have a little bit more than 1 second for every position. So you have to measure 3 spectra in 1 second, and the only way you can do that is to use array spectrometers. And I want to discuss a few problems that these spectrometers have. Suppose you want to measure transmission, and what you then have to do, you have some light shining on your glass, and you have to measure how light goes through. And so that's basically the task of a transmittance spectrometer. In reality, it looks like this. You use a light source which has a certain spectral intensity distribution. So here, this is the wavelength scale. Typically, spectrometers used for production control cover the range 400 to 700 So the visible, that's the most important spectral range for characterization of glass coatings. In many cases, they also extend to the near infrared, up to 900 or 1000 nanometers, and sometimes also a little bit into the ultraviolet, but not too much. Well, anyway, the light source here has a certain spectral distribution that we usually don't know. Then you have the interaction with the sample, in the sense that the sample transmits for every wavelength a certain amount of radiation. That's actually what we want to know. That is the information we can get from transmission spectroscopy. But it's not directly available, because then afterwards the light is detected by a spectrometer with many detectors. Each one is responsible for a single wavelength, so you have a few hundred detectors here, and each detector has its own sensitivity. Usually in the near infrared it's 0 if you use silicon detectors. There's the band gap of silicon, and there's no absorption above 1100 nanometers. There's a maximum usually in the visible, and depending on some details, a certain substructure, and less sensitivity for ultraviolet radiation. And in the end, if you multiply the light source spectrum by the sample spectrum and the spectrometer spectrum, you get the raw signal here, which depends on all three of them, the spectrometer, the sample, and the light source. But we are not really interested in getting information about the spectrometer or the light source. We only want information about the sample. So somehow we have to extract, we have to cancel out somehow the light source and spectrometer properties. And we can do that by doing a reference measurement. In transmission, that's pretty simple. Basically, you take the light source. Here I just sketch a typical system where you have light source emitting from here, and you generate a kind of light beam. And well, everything that comes here depends on the light source, the mirrors, filters, lenses, whatever, fiber properties. Then it goes through the position where normally the sample is, but if there is no sample in the reference measurement, or the so-called 100% measurement, then there is nothing here that can absorb or redirect radiation. So the transmittance here in this position is 1 or 100%, and then we detect on the detection side with lenses and fibers and whatever we need to detect radiation. So we do this measurement, record the raw signal, and then we enter the sample and measure the raw signal again, and then we divide the two, and this way we can cancel the basically the detector and light source properties. Actually, there's a little bit, there's a small complication more, which I did not mention up to now, which I would like to mention on the next slide, which is a live demonstration of a so-called virtual array spectrometer. And here I would like to discuss what can go wrong if you do those measurements. And we have to start here on the left side with the so-called dark signal. That's what I have not mentioned up to now. Every detector that you use, and in an array spectrometer you have several hundreds of those detectors. Every detector generates a signal even if there is no light. It's basically a thermal effect, and it depends usually on temperature, in the sense if you increase the temperatures, then the dark signal is larger. And also the dark signal is a little bit noisy usually. Here in this very simple simulation, I have assumed that the dark signal is more or less the same for all pixels except for the noise. That is not really realistic, but well, this is just a simulation, a demonstration example. And if I change the temperature of the detector of this array, you can see that the dark signal changes. Just concentrate here on this graph. So when we do the measurement, actually we have to measure the dark signal in order to subtract it for everything that we measure then afterwards. We have to make sure that we know the temperature of this detector. If the temperature rises, the dark signal will rise, and that might generate a problem. Let's suppose we start here with 300 Kelvin at room temperature, and we have this dark signal that we record and store it somewhere. Then we do the reference signal, the 100% measurement, and in that case the temperature might be different, the temperature of the detector, and let's assume that the temperature is the same, 300 Kelvin as well. Then there is a second temperature which is important, which is the temperature of the light source. In most cases, we are using a halogen light source, which gives a broadband spectral distribution of the radiation. And that is very dependent on temperature. A halogen light source is basically a hot piece of metal, and it emits like a black body radiator does, very strongly dependent on temperature. So let's assume we have a certain temperature here, very high usually. You can see if the temperature is too low, then our signal is weak. There's almost no light in the blue. So in order to do spectroscopy here, we have to have a large signal, as large as possible, and with a high temperature we can increase, in particular here, the fraction in the blue. Suppose we have this temperature, 3139 Kelvin, and then we do the reference signal. So we have stored the dark signal, we have stored the reference signal now, and now let's take the spectrum, the signal of the sample, and ideally we have the same temperature. Let me try to set the same temperature here. That's only 2 degrees or 2 Kelvin difference. That should be okay. Then we have the raw signal here, and now if we divide the raw signal by the reference signal, we get the transmission. That's the blue curve here, the transmission spectrum. And the green line shows the ideal spectrum that we should measure. That's the property of the sample. And here you see that, well, yeah, we have some noise, but basically we reproduce the green curve fairly well. So what can now go wrong if you do those measurements? The worst thing that can happen is that the temperature of the detectors, the temperature of the light source here, when you do the sample measurement, is different from the temperature of the light source when you do the reference signal. That means you have a drifting light source which changes its temperature, and suppose the temperature gets higher during the measurements, then you can see you get a totally wrong spectrum. The shape is okay, but we are far too high, and this would lead to very wrong conclusions. I will show an example later on. So if the temperature is too low, then we measure a transmission signal which is too low. So ideally we should have the same temperature as close as possible, and here 2 Kelvin difference is already noticeable here in the level already. So the temperature of the light source must be extremely stable. Usually you do that by waiting long enough, you switch it on, and then you wait something like 10 minutes or 15 minutes, and then the temperature should not change too much. And the second thing you should do is you should measure the reference signal and the sample signal with a small amount of time in between, usually after every pane, after let's say 40 seconds or 60 seconds, your cycle time, you should measure a new reference, so that the distance between distance and time between those two measurements is only a few seconds or just a minute, and then it should work. Okay, there's also the problem of the detector temperature. Let's say if the detector temperatures are not the same, then you will get a problem like this. Let's say usually only at the edges here where the noise becomes relevant, you have the influence of the dark signal. Suppose the dark signal at the detector temperature at the reference measurement was higher, then what you will find is that here at the edges, basically the cancellation of the detector properties doesn't really work out. So then you have to throw away this part because you cannot trust it. Usually that's not a big problem because at the edges here you have a lot of noise anyway, and maybe you should never trust this range too much. But nevertheless, you should take care of temperature stabilization of the detectors as well. So you should avoid that they heat up or are cooled down accidentally in your factory, which would generate a problem in the quality of the spectra. Okay, let's go on to reflectance. In reflectance, we have an additional problem. If you want to do the cancellation of light source and detector properties by doing a reference measurement, there's the problem that you don't get any signal if you just leave out the sample. Instead, you have to use something which reflects in the same direction as your samples do, but you have to know how much it reflects. So you need a reference mirror or a so-called calibration mirror. That means you need something where you know exactly what the reflectivity is for every wavelength, and then you can use this for a calibration. So you detect the reference signal here in order to do this kind of calibration. Then you put in your sample instead of the reference mirror, measure again. Then you divide the raw spectra of the sample and the detection, the reference sample, and then you multiply by the known reflectivity of the reference mirror. This way you get the true reflectance of your sample. And so in this case, the calibration is a little bit more difficult in a large area coater because you cannot easily bring in a reference mirror where the glass is usually, because if the float glass is moving, it would be probably dangerous to put a reference mirror in between. If you are not fast enough to move it away, then the next glass will crash into your reference mirror. So what you usually do in the case of reflectance, you move out the whole system to the side, away from the coating line, and do the reference measurement at the site where you have enough time, and then you can move back to the line in order to measure the next glass. So this requires the motion of optical components on a traverse system. And usually you do that only at the end of the coating line when you have a traverse system anyway to measure at different positions on the glass. Okay, now you have, ideally at the end, you have two reflectance spectra, the film side reflectance, the glass side reflectance, the transmission. And if you use modern equipment, you can have quality like this, almost noise-free, very nice curves, which look very solid. But unfortunately, if you have to ask yourself, or if you have to answer the question, which layers should I change, or what should I change? Is everything okay? you don't get any answer from those spectra. So you have to do a little bit more. What is easy to be done is to compute color values. And this is important anyway because color is a selling property. So you have to produce a certain color, otherwise you cannot sell your product. And so measuring color means you take the optical spectra and you do a kind of integration. You basically multiply by the sensitivity of the human eye sensors, and then you get typically three numbers, in most cases called L star, A star, B star, and this L star characterizes the brightness, and A star and B star how much blue and how much red is contained in these spectra. So these color values are there. They can be easily computed from the measured spectra, but they don't really give the answer that we have to know. What do we do if these colors are different from the target values? We have target values for the colors. We have seen that in the design. There, the wanted A star and B star values were the target values for the optimization. So we know what color we want, but what do we do if the color is not correct? That's the question that many poor operators have to answer all day long. And that's a real difficult question. Suppose we are producing at the moment, the spectrometers tell us, well, this is the reflectance color, this one here, that is what we produce now, but here is the target color. So we are off. We are a little bit too high, a little bit more far to the left. So we have to correct our coater in order to bring this dot here into the target area. And you can do that by trial and error. You can do that by a little bit of experience. And suppose your experience tells you, okay, let's tune the base oxide. Actually, we don't know how the absolute thickness values are at the moment, what the values are. We just switched on our coater, and we just can do relative changes. So 1 is in the middle. Now 103 means 3% thicker base oxide. Suppose I would have buttons to increase the base oxide thickness, and we can watch the blue color dot. Yeah, it's moving into the right direction. We can tune the center oxide a little bit. Oh, that was a little bit too much. I have to go back slowly. So now we are in the target area. Very nice. So 18% more base oxide does the job, and maybe a little bit more center oxide. Fine, let's do that. Wait, let's go back. I show you another option. So we can go back to the initial values and increase one of the silver layers, maybe, or decrease. No, that doesn't move us into the right directions. Okay, this one also works. So the second silver layer increase by 7%, also brings us into the wanted area. So we could change the oxides, or we could change the silver layers, and there are probably many other combinations possible. So obviously, this change in color is not unique. It depends on the layer thicknesses that we have, on the absolute values, on the coating that we produce, but unfortunately we don't know what coating we are producing, what are the absolute values of the thickness. So now our decision what we should change in the coater is very, very unsafe, and I call this color gambling. So if you just look at colors, then it's very unsafe to control your coater just based on color values. and I show you here an example. There is a double silver coating here on the left side, which leads to L star of 49, A star minus 0.8, and B star minus 10.27. On the right side, it's a different coating, the same layer stack, but different thickness values, producing exactly the same A star and B star values. So they would be considered to be the same. L star is a little bit different, but usually that is not too important for production. But the spectra are very different. There's the red and the blue spectrum. They are clearly very different, but they lead to the same A star and B star values. So actually, by looking at color values, you throw away a lot of information. Color computation means averaging, and so you throw away information that can uniquely identify your coating. And I will show you in the next slide how we can do the transition. So here we have two spectra which produce the same A star and B star values, and but the spectra are clearly very different. So if we tune our thickness values, the oxide values, and we generate a different bottom oxide and a different center oxide, and then probably we do the rest automatically. We can, by changing different thickness values here, changing the thickness values, we can make the smooth transition from one spectrum to the other. They had originally the same color values. Now they have the same color values again, but now we have a unique setting of the thickness values. So the layer thickness values are really different for different coatings, although they have the same color. But if we take the complete spectrum here as information, we can never do that with wrong thickness values or with two different layer stacks. It's very, very unlikely that they produce exactly the same reflectance and transmittance spectra. So if we do what's called optical modeling, if we try to reproduce the measured spectrum by our model spectrum, then we have uniqueness. We have uniquely determined the thickness values, and so now we know what we are producing. This is much, much better than just taking color values as guidelines for running the coater. So, ideally, we should have as many optical measurements as possible. So in order to run the coater in a very, very safe way, we would take a complete scan of the glass after each deposition stage. Actually, each deposition stage is not really known when you switch on the cathodes. So you should measure what has been deposited immediately after the deposition for every position on the glass. And if we do that for every cathode group here, or in between every cathode group, we would have complete information about what we are doing in our coater. That would be the ideal production control, but unfortunately this would be really very expensive, and it would also be very problematic or very difficult, because to run a traverse with reflectance and transmittance measurements in vacuum is still very difficult and almost impossible. I have never seen a solution like this. Would be ideal if it would be also cheap. But, well, let's say goodbye to this dream and take a look at the real situation. In many coaters, we have at least transmission measurements in between the cathode groups, sometimes up to 10, sometimes 4 or 5. So that is achievable and doable and it is sometimes expensive, but not too expensive concerning the operation of the very expensive large area coater. So here I would like to mention that in this demo there is a T0, that is a transmission measurement of the incoming glass before the deposition starts. In most coaters that I have seen, people left this out and thought they could save some money there, but I will show you in a moment that it is important to have a measurement here. Then you have transmission measurement after every basic deposited layer, basically deposited layer. So in the end, outside of the vacuum, you have the traverse system that I mentioned already that scans across the glass and measures 3 spectra. So let's take the measurements seriously. Let's start with T0. That was the transmission measurement of the uncoated glass. Typically, if you have float glass, it looks like this. The transmission is highest in the green in the middle of the visible, and then towards the blue it decreases a little bit, and in the near infrared here around 1000 nanometers you have the iron absorption, so that decreases also. And in the tutorial about handling glass substrates, I have shown you that we can use a float glass model to describe the optical properties, and here actually I only vary in this modeling, I only vary the absorption bands, the weak absorption bands, and I don't touch the basic properties of the glass, so the real part of the refractive index is almost the same in any case, but the small absorption differences that you have from glass to glass, they can be accounted for by these oscillators here. And these can be fitted, these can be fitted in a few seconds. Typically, you need 1 to 2 seconds for this, and then you know the absorption coefficient of the glass. And if you do that for every glass, you will find there are slight differences if you send in glass. Even if it's from the same batch, the individual panes will have slightly different absorption coefficients, and that can be important for the following fits. So with these T0 measurements, you can characterize each pane, and later on I will show you that it makes sense to write down these values for every pane and load these values again when you want to do thin film analysis on this substrate. Okay, let's take the next, or one of the next propads. This is measurement T2. The base oxide is more or less finished, and here I just show you as an example the fitting of the titanium dioxide thickness. So we can do that manually here, and we can also do it automatically. So what you see here is that the thickness is very well defined. The fitting is very easy. Typically it takes a fraction of a second only, and so it's very quick. But I want to show this quick and simple. I want to show in this example how important it is to have very good measurement quality. Here with this bar here, I can change the error in the transmission measurement. Basically, I multiply by a constant factor, and just recognize when we do the fit here, I press start, we get 20.7 nanometers for this titanium dioxide thickness. Suppose we are measuring the transmission by 1% wrong. Let's say we have an error of 1%, then this difference here is clearly visible. If we do the fit again, we get 22.5 nanometers. This is almost 10% more. So a measurement error of 1% by misalignment, for example, or temperature change between reference and sample measurement would lead to a 10% error of thickness. And this is actually much too much. If we get a measurement error of, let's say, minus 10%, that would be a tenth of a percent, and we can do the fit again. Then we measure 0.2 nanometers below the true value. So basically, this would be 1% error in the thickness. So with a tenth of a percent error in transmission, we get about 1% error in the obtained fit results. And this is what we can just tolerate. Usually it should be even a little bit better. So the transmission measurements have to be good on the level of 0.1%, which is possible, but which is not easy. Okay, let's go to the next station. This is where we have the first silver layer, and since we know the coating that has been produced up to now, analyzing the previous probe heads, every little extra fit here is very quick, because it's only usually one or two fit parameters that you have to change. In this case, the damping constant of the electrons and the thickness of the silver layer. And so fitting usually means being ready within half a second or so. So it's very easy to do this inline fitting analysis because we are doing very simple steps, one after each other. Let's take a look at some results. If you take these inline measurements seriously, here you have, for a single silver low E, real production data from one of my customers from the start of the production to for 360 paints, and you can see the silver thickness here versus paint ID, the bottom oxide and the top oxide. And here the top oxide thickness jumps. Obviously the operators have made some changes in the settings. Here they decided to take it back. Here they did something, tried something again. And let's take a closer look at the silver curve here. In the case of silver, only the first pane was clearly off. The target value here was 12.3 nanometers, and with the first pane, the inline probe head said, well, 11.7. The operators then decided to increase the power by 5% or so, and then the second pane was already very close to the target value, and from then on they produced the right silver thickness. In the long time behavior, you can see that the silver thickness monitored by the optical production control slowly decreases. I'm sure this is caused by the target erosion, and so it goes from maybe 12.3 something to 12.3 or below, 12.8, 12.28, something like that. And here the operator decided to change again, I guess, the power to increase the thickness again. So you can see very slow, very small trends, and you can do the appropriate actions in order to stay on target values for everything that concerns your coating quality. Okay, let's take a look at the exsitu traverse measurements. Here, this is now the first chance that we get information about position-dependent coating properties. And what you get typically are 3 spectra, hopefully in the same quality as we have discussed up to now. And if you have a double silver coating, you have basically 5 thick layers: base oxide, center oxide, top oxide, and the 2 silver layers. And if you do the fitting of all those 5 layers, and you get a high quality model in addition to the high quality measurements, then you get reliable values for those 5 thickness values, and you can present thickness profiles to the operators. Here are the thickness profiles, thickness versus position on the glass for the top and bottom silver and for all the oxides. And from these curves here, from these thickness profiles, the operators can draw conclusions and change gas flows or power settings in order to make these profiles as even as possible. Okay, just a remark about triple silver. If you do the analysis, you will find that if you have 7 thick optically important layers, you cannot get all those 7 numbers from the traverse measurements. It's not possible. The errors are much too large, especially for the base oxide. So what you have to do in order to tune your coater, you have to separate the problem. And my proposal is to switch off all the cathodes except the first 2, the base oxide, the first silver layer, run a test pane, get the profiles for the first oxide and silver, try to make it as even as possible, and then freeze these profiles and switch on the other oxides and then produce those oxides and get those 5 numbers from the measurements, knowing the first 2. So this is a little bit more tedious, but triple silver is more difficult in many aspects, and this is one of those aspects. So in the end, I recommend to display the current state of the coater to the operators in different ways, in intuitive ways, and this is one example where you give clear recommendations for changes of, let's say, the 5 layers of the double silver coating, where the operators can see, okay, the center oxide should be thinner by -5%, and then they can decide what they change in their coater. But there can be many different kinds of displays which can be useful and to provide the information that can assist the operators in making the right decisions. Okay, that was this more or less overview on production control. I will generate another video tutorial about our brain software, which does exactly what I have shown you today, and I can give you a simulated production demo showing how brain can be used to do what I have shown you here today. And I will prepare this video during the next 2 or 3 days, so you can watch it on the next weekend. Okay, thanks a lot for your listening today. See you soon.